Okay, so today we're going to deal with section 3C from your book, and it talks about dealing with uncertainty. The main aspect of this section, or the main topic in this section, is error and significant digits. So, significant digits basically, a lot of times they're used to tell. So, somebody, if they write their work out, they want someone to know how accurate their work is. So, a lot of times they will, even if a zero is unnecessary for the number, they'll put a zero there to tell somebody, I calculated it up to this point. So when you're talking about significant digits, you're trying to identify what someone thinks was important for this number. Okay. So these are some rules that you need to write down and just be, 100% sure of how it works. So non-zero digits. So any number that's not a zero is always significant, right? We don't even have to look it up. We know. So if I write like 725.32, this would have five significant digits. No question, any digit that's not a zero is automatically significant. Okay. Then we have zeros that follow a non-zero. So zeros that follow a non-zero digit and lie to the right of the decimal point, as in 4.20 or 3.00. Those are always significant. Now think about the reason for that. Why would somebody tell you 3.00? Why would they write that number when they could have just said 3? So that's what it means to be significant. That means in order to talk about this, whoever was writing this wanted you to know that they calculated it and or rounded or calculated or measured those two decimal places, and they actually got zeros there. So the thing is, they could have just as easily written 3, but they want to pass on the knowledge that they actually checked, or if this was a measurement, that they used two decimal places of accuracy and they just both turned out to be 0. So this actually has three significant digits, right? So right here, the number 3.00. Now, how many significant digits are there in 4.20? There is also three significant digits, okay? So what if somebody came along and they wrote, 5.30000. Okay. Now, why did they write all that? They could have just written 5.3 and it would be worth the same, right? 5.3 and 5.30000 is the same number. However, they're trying to tell you that they measured also here. It just so happens that they got four zeros there. So this would have one, 2, 3, 4, 5, 6 significant digits. So this would have 6 significant digits. Okay. So zeros to the right of a decimal are significant, and they're always significant. Okay. Zeros between a non-zero digit, as in 4.002 or 3.06, or other significant zeros, such as the first zero, 30.0. Those are also always significant. So if I wrote 4002, this has four significant digits, okay? Because anytime there's zeros in between non-zero numbers, you automatically count those as significant, okay? So these are the always significant category. Now we have never significant. Zeros to the left of the first non-zero digit. So 0.006, that has one significant digit. 0.000052, that only has two significant digits. So zeros to the left of the first non-zero digit, okay? So, and a lot of times that happens with decimals, right? Now, again, the difference here is that this zero was in between two non-zeros, a 3 and a 6. So that's why there were three significant digits for that one. Now, for this one, there are all these zeros and then a 5, 2. So anything to the left means that we don't count it as significant digits or zeros to the left, I should say. Okay. Zeros to the right of the last non-zero digit, but before the decimal point, as in 40,000 or 210. So 40,000 is one significant digit according to this, right? 210 is two significant digits according to this rule here. So it says zeros to the right of the last non-zero entry. So here's the right, or here's the last non-zero entry, and this is a 0 to the right of it. That one does not count. Those are not significant zeros, okay? So let's practice this a little bit with some of these, okay? So here it says, state the number of significant digits and the implied meaning of the following numbers, okay? So take a minute, pause the video, come down here, and try these. Try to figure out how many significant digits you have, and maybe write out some reasoning as to why there you feel that way. Which one of these cases is it? Okay. All right. So you have the video unpaused now, and it says, so we have 1, 2, 3, and now is this 0 significant? Well, if I didn't put that 0 there, it would be 11.9. But by me putting the 0 there, I'm telling somebody I measured this decimal place as well. I just happened to get a 0, or I rounded off to get a 0. So what I'm going to say is that this has 4 significant digits, okay? And it implies the measurement is let's say that, let me write this a little bit better. 4 significant digits implies a measurement. There we go. I was using bad English. Sorry about that. A measurement to the nearest hundredths. Oh, but it's in seconds, so nearest 0.01 seconds, or to the hundredths place. Because they're saying 11.90 seconds. And why did they put the 0.90 there? Is they're telling you that they are that accurate within 0.01 seconds, okay? A length of 0.000067. So remember, we talked about these zeros not meaning anything unless somebody tells us otherwise. So then we're just going to say 2 significant digits, okay? And let's see here. 2 significant digits and implies measurement, a measurement to the nearest 0.000001, okay, meter. Okay, so this measurement goes to this place value, okay? But what they're saying is that, now we didn't do this, this is in your book, but I didn't give you a measurement like this, but you could technically write this as 67 micrometers. That's just another measurement from all of the, remember when we did all the conversions and everything like that? That was just another measurement we didn't use a lot of. But you could rewrite 0.000067 meters as 67 micrometers. So they're just trying to show you that these 2 digits are all that really matter. There's another way you could rewrite it without those zeros, okay, if you just change your labels. All right, let's look at part C. So part C, let me see here. So these 3 zeros are not significant, right? But this 0 and that 3 are. So we're going to say 2 significant digits. Okay. And we know that the leading zeros are not significant, but they're just placeholders. So leading zeros are just placeholders. And if we really wanted to, we could rewrite as, how many grams? So this is 0.0003 grams. We could rewrite that as 3.0 milligrams, right? Because remember, if you're at G grams here, milligrams is 1, 2, 3, right? So this would be milli. The next one would be centi, and the next one would be deci, right? If we did our little conversion. So it takes 1,000 milligrams to equal 1 gram. So I can move the decimal 1, 2, 3 and change this into a milligram. Okay. But the reason I wrote 3.0 is because there was 2 significant digits. So again, they're telling us that 3 and that 0 at the end is important, but the zeros on the left side of 3 are not. So once again, we're using this rule right here. This one right here, zeros to the left of the first non-zero entry. And then at the same time, we also used zeros that follow for the 0 that's at the end. So that's why I ended up with 3.0 milligrams. So notice this is equivalent to 3.0 milligrams. Okay, they're the same thing. There's no difference. Now, they didn't ask us to convert it, but I think in the homework, they kind of sometimes ask you to just write your answer in terms of a different notation. So just be ready to do something like that. It says a population reported as 240,000. We know this is 2 significant digits because we have these 2, and then these zeros are not significant. And we know that this is a measurement, implies a measurement to the nearest 10,000 people. Okay. And once again, we have a population reported as 240,000. Okay. So this is 100,000s. This is 10,000s. So 10,000s is the smaller of the 2 values. Okay. So that's what we're going to use to tell how close we are to our actual answer. Okay. So 2 significant digits. Let's do one more. A population reported. Oh, this is the. Is this the same one? Let me go back. I kind of want to make sure I didn't get lost. Oh, okay. So this is a new one. So they use scientific notation for this, but notice there's 3 significant digits. So this is 2.40 times 10 to the 5th. Well, that is 3 significant digits, right? But the number means 240,000. Okay. So this number and this number are the same. And that's why I got confused because this number only has 2 significant digits. This number has 3 significant digits. Why? Because they wrote it, they could have easily written this, correct? They could have written 2.4 times 10 to the 5th, and that would be the same thing, right? They could have just as easily written that, but they chose not to. They chose to write 2.40. So that's telling you there's a reason they put the 0 there. It's significant, right? It wasn't necessary. It was significant. So they're telling you that whatever you do, even though this number means that, which means the same as this one, they didn't give you any added information. So you just have 2 significant digits. In this problem, they specifically wrote it with 2.40, even though they didn't have to. They're telling you that that 0 is significant for this problem. Maybe they, spent a lot of time making sure their measurement was accurate to within that value. So this has 3 significant digits, and it is, let me see here, implies a measurement to the nearest. Now this one means that they measured even better, to the nearest 1,000 people. Okay, so notice once again, it's the same number as up here, but this one only implies a measurement accurate or within 10,000 people, or to the nearest 10,000 people. This one's a little better. It's accurate to within 1,000 people, because this extra significant digit tells you that they took the time to be that, to go that extra distance or that extra measurement to make sure that they were, I guess you would say, accurate. Okay. So again, hopefully that's a good little background for you guys on significant digits. Okay. So here's rounding with significant digits. For each of the following operations, give your answer with the specified number of significant digits. So we have 7.7 millimeters times 9.92 millimeters. Give your answer with 2 significant digits. So what I'm going to do here is, where did A go? Oh, did I delete it on accident? Okay, so I'll just do A here. So 7.7 millimeters times 9.92. So in general, you don't do any rounding until after you're done. Oops, 9.92 millimeters. Okay. So when I take out my calculator and I multiply this, let's see what I get. Let me get out my calculator real quick. So on my calculator, I'm going to do 7.7 times 9.92. And it gives me 76.384. However, they only want me to write my answer with 2 significant digits. Well, that's these 2 guys right there, right? So then I'm going to say that this is 76. Okay. Let me double check and make sure I'm doing everything the way they want. So, and then our label, well, what's millimeters times millimeters? Well, that would be millimeters squared, right? So this is 76 millimeters squared because I could only use significant digits. So I had to round the 6. Either I round the 6 back to a 6 or I round it up to a 7. The 3 tells me where to round. It tells the 6 to stay at 6, okay? Now we have 240,000 times 72,106. So let's do that, 240,000 times 72,106. Let's see what we get. 240,000 times 72,106. And I get on my calculator 1.730544 times 10 to the 10th. Okay. So they tell me that I get this massive number, 1.730544 times 10 to the 10th, but they only want 4 significant digits, okay? So what I do is I do 1.730. Now the 5, oops, that's already, sorry about that. Here's 1 significant, 2 significant, 3 significant, 4. So that 0 has to either round up to 1 or stay at 0. Well, the 5 tells me, the 5 which is to the right, tells me to round up to 1. So this is going to be 1.731 times 10 to the 10th, okay? And that has 4 significant digits. That's what they asked me to round with, okay? So this is how you can do rounding with significant digits, okay? So now let's talk a little bit about error. And once again, if you have questions on this, we can talk about this in our next meeting in terms of significant digits. So random errors occur because of random and inherently unpredictable events in the measurement process. So that's basically saying ones you didn't know that could happen, not necessarily your fault. Systematic errors occur when there is a problem in the measurement system that affects all measurements in the same way, such as making them all too high or all too low. So again, I have, for an example, I have a scale that actually weighs me about 2 pounds less than I actually am, but it's always 2 pounds less. So, you know, if I went to the real scale versus, you know, or accurate scale to this scale, it always weighs me two pounds less. Okay. So in that sense, it consistently is wrong, but it's always the same amount wrong. So that would be a systematic error because everything will always be measured wrong. It'll always be that I weigh a little bit less than I actually do in real life on the scale. Okay. So size of errors. There's such a thing as absolute error and relative error. The relative error is very straightforward. The absolute error basically says that it's the measured value minus the true value. Okay, so what this means is people are oftentimes going to make predictions or claims, okay, and then you're going to compare that to the actual or true value, okay, and you subtract those two. So in the example we're going to do, it'll be pretty straightforward, but the book actually writes it a different way than I do. So we'll just go over this real quick. So, and then relative error, remember anything with relative is basically always compared to something else you divide. So it says the relative error compares the size of error to the true value. So you take your absolute error that you found up here and you divide it by the true value, okay, whatever it was supposed to be. or whatever it actually is. All right. And then you multiply it by 100%. So we've done a problem, I think, like this in a previous section. So anyway, let's look at this example. Find the absolute and relative error. Projected budget surplus of 17 billion turns out to be 25 billion at the end of the year. Okay, so let's find the absolute error. Okay, so what is the claim? Well, in this case, the claim is the projected 17 billion. So what I would do is I would say my absolute error is measured value. So let me see here, projected budget. Find the absolute and relative error. Projected budget of surplus of 17 billion turns out to be 25 billion at the end of the fiscal year. So this is kind of a tricky one. In your book, this is how they want you to do it. So real quick, let me show you what your book does, and then I'll just kind of show you the way I think about it. In different math classes, when you talk about absolute error, it doesn't matter if it's positive or negative. What matters is how much. Okay, so they normally put absolute values around it. So that's why I almost want to put absolute values around this, and I only care about the positive. But in your homework, I did see sometimes that it was a negative value. So what they're saying in your book is that the measured value is 25 billion minus 17 billion. Okay, so this is not how I read it. Okay, so I end up getting 8 billion. So this would be, according to your book, this would be our absolute error. But my problem with this is I feel the wording is bad. So it says find the absolute error and the relative error, projected budget surplus. So to me, projected means like a claim, like you think that that's how much it is. Well, according to that, claimed. But the actual value lies from the true value. So we actually got 25 billion budget surplus. So the actual budget surplus was 25 billion, but the claim was 17 billion. So this should actually be opposite. This is how I would do it. Now, if the meaning is that the budget surplus, if you're talking about the projection as the actual thing, then I guess I could see it, but it just sounds too confusing that way. So I would have done it this way. I would have done absolute error equals 17 billion, because that's what they claimed through the projection, minus the true. What we ended up getting was 25. That was the true value. So I would have got negative 8 billion. But again, I don't really care, because to me, absolute means always positive. What we really care about is the difference between them. We don't care if it's positive or negative. We care about the difference. But I think in your homework, sometimes they do care about the negative. So I'm just trying to show you this. Okay. Just so you can kind of see, if you're like me, you kind of read it differently. And we can talk about it. If you're having trouble in the homework, we can talk about it. So relative error, you take your absolute error. So we got 8 billion, if I do it the book's way, divided by the true error, the true value, which was, we said 17 billion. Okay, so then this would be 8 divided by 17, and let's see what they got. They got 8 billion divided by 17 billion is approximately 0.471, which is 47.1%. Okay. So let's say we did that. Now, the only difference between this and the other one is if you were doing it with my value over here, you would have ended up getting relative error. You would have ended up getting negative 8 billion over 25. Yeah, 25 billion. So it really depends on the wording. So I'm going to try, when I give you guys the homework, and when I'm also going to give you the quiz and the exam, I'm going to try to give you ones that are very straightforward, where it's obvious one is a claim and one is a certain amount, and then the other one is the actual value or the true value, because I just don't like the way that this one seems to work for this particular problem. But I wanted to go over it because I don't want you to run into the same problem that I did. So this would be 0.32 or 32% negative. So this is basically saying that it was an over projection or an under projection. They projected that it was going to be 17 and we ended up getting 25. So we under projected by 32%. Okay. This one, they're counting the 25 billion. They're counting the 25 billion as the measured value, which I don't agree with. I feel like it turns out to be 25 billion means that that's the actual correct amount, and the 17 billion was the claim. So I would have preferred this method. So if you run into this problem on the homework, please ask me about it and I'll try to bring those up and we can go over it as a class. Okay, so accuracy describes how closely a measurement approximates the true value. An accurate measurement has a small relative error. Precision describes the amount of detail in a measurement. Okay, so combining measured numbers. These are just, by the way, these are just definitions you want to write down. We'll use them in a little bit. And I think in your homework, they ask you what's more precise. So it describes the amount of detail in a measurement. So that would be, you know, how many digits of accuracy. And then describes how closely a measurement approximates to the true value. So one of them is like saying how accurate it is, I guess, in terms of the measurement itself, and the accuracy is talking about your measurement versus the true value, how close it is to that. You know, that would be your accuracy. Okay, so one is about an error and one is about a measurement. So combining measured numbers, rounding rule for addition or subtraction, round the answer to the same precision as the least precise number in the problem. So you can't be more accurate than your least accurate. Kind of like that old saying, a chain is only as strong as its weakest link. That's the same with this. You have to use the weakest level of accuracy for your final answer accuracy. Okay. So round the answers to the same precision as the least precise number in the problem. Rounding rule for multiplication or division, round the answer to the same number of significant digits as the measurement with the fewest significant digits. So very similar idea to this. These both are, you know, basically saying the weaker of the significant digits or the weaker level of precision, that's what you use for your rounding. And then avoid rounding early in the problem. Don't do it till the very end. Okay. Let's see how much we got left. Only a little bit. Okay, good. All right. So it says a book written in 1985 states that the oldest Mayan runes are 2,000 years old. How old are they today? So let's just say, so this is the year 2020. So right now, current year, we're in 2020, right? So currently we're in 2020, okay? So it says a book is written, how old are they now? So technically, in 1985, we would do 2020. 2020 minus 1985, right? And we would get 35 years, okay? So that means the book is actually 2,035 years old. That's how much we would think, right? Is this correct? So do you guys think that this is the correct way to do it? If a book was written 2,000 years ago, and in 1985 I told you, hey, the book is are 2,000 years old, and then in the year 2020, which is 35 years later, now would I say the book is 2,035 years, or would I still try to say 2,000 years old? So this is what these are trying to talk to you about in this rounding and this accuracy and this precision. Okay, so what we're going to do is we're going to think. Okay, so let's go down here. Let's think about this real quick. Okay, so a book written in 1985 states how that the oldest Mayan runes are 2,000 years old. Okay, so we say a book is written in 1985 is roughly 35 years old. So roughly 35-year-old book, right? If we're reading it now, okay? So our temptation, we are tempted to say the runes are 2,035 years old now. Okay, that's our temptation because the book is 35 years. Why not just add it to it? Okay. However, there's a problem. 2,000 years is less precise than, or is the less precise, let's say it this way, less precise of the two numbers, right? So remember, this one is measuring, right, 35 years. This one is measuring, let's say this. 35 years is measuring to 1 year accurate, right? So if I say 35 years, that is, down to the ones place, okay? If I say 2,000 years, that is measuring by thousands of years, right? So this one is accurate. 2,000 years is measuring I forgot how to spell measuring. Oh man, measuring. Well, I guess I was right the first time. So I wrote it right the first time. Sorry, guys, I can't spell. Measuring by 1,000 years. So which one of these is the least precise? The one that measures 1 year accurate or 1 year at a time, or the one that measures 1,000 years, right? So the one that measures 1,000 years is the less precise or the least precise of these two numbers, okay? And then up here it says, if you're using precision, rounding rule for addition or subtraction, we can't just add 35 years to that because it says round the answer to the same precision as the least precise number. So the least precise number is 2,000, right? And it's accurate, or it's measuring in terms of thousands of years. So what we have to do then is we have to say the book, or sorry, not the runes. The runes are 2,000 years old. Okay, so that's what we end up needing to say. Even though we feel like it should be 2035, but we can't add that level of accuracy because then you're telling somebody that you have now measured the runes accuracy to within 1 year. But in reality, they said that the runes are 2,000 years old. Do you think it's exactly 2,000 years? Or do you think that that is their best approximation? That's their best guess for how old, give or take, right? So if they wanted to be more accurate, they would have said 2,005 years old or 2,100 years old. They would have been more accurate. They would have used more significant digits. Because they only used 2,000 with a precision of 1,000 years, that means that we have to kind of stick to that because that's the least precise of the measurements. Okay, hopefully that makes sense. So that's what we have to stick with, even though we want to say this, right? We want to say that it's 2,035 years old. That would be implying that we've added a level of accuracy to the measurement of how old the runes are. But we don't actually know the exact amount because they told us 2,000 years. Okay. And in 5 years, is it now going to be 2005? They didn't give us that level of accuracy, okay, or precision. Sorry, I keep using the word accuracy when I should be using the word precision, okay? So roughly 35 years old. So what we need to say is, oh, I wrote it up here. Sorry, I should have wrote that down here. Let me write that. I got sidetracked. The book is 2,000. I'm sorry, not the book, the runes. I did it again. The runes are are 2,000 years old. Okay. So hopefully that kind of helps you guys with the whole precision aspect. You can't be more precise than your least precise measurement. Okay. Let me see if I want to do this one. A government in a town of 82,000 people plans to spend 41.5 million this year. Assuming all the money must come from taxes, what average amount must the city collect from each resident? So let's see. Okay. So we're going to do division. So it says, assuming all this money must come from taxes, what average amount? So remember, whenever you're asked to average something, you have to divide it. So it says the government in a town of 82,000 people plans to collect 41.5 million. So we have 41.5 million divided by 82,000 people. Okay, so we're going to take 41.5 million and divide it by 82,000 people. Let's write this a little bit better. 41,500,000. So I'm getting rid of the 41.5 million and I'm writing it as what it is. $41.5 million. And I'm dividing it by 82,000 people, because they want to know what average amount must the city collect from each person. So we want to know how much money each person has to do. So I'm going to take 41,500,000 and I'm going to divide it by 82,000. And I should get approximately 506.097561. Okay, so here's the problem. Okay, it says assuming blah 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 blah, what is the average solution? Okay, so here's the problem. They told us that 41.5 million, that has 3 significant digits. 82,000 has 2 significant digits. So what we do is we go up here and we kind of look at our rules for dividing. It says rounding rule for multiplication or division. Round the answer to the same number of significant digits as the measurement with the fewest significant digits. So of these two numbers, we're going to look at this. Which one has the least amount of significant digits? 82,000, it has 2. So that means my answer must also have 2 significant digits. So if I rewrite this as $510 per person, how many significant digits does this have? Well, here's 1, 2, and then remember the 0 at the end doesn't matter. Okay, so this has 2 significant digits, and we would be collecting $510 per person for these purposes of taxes. Okay, so this is, again, this is the actual decimal, right? How many digits it gave us, but because 82,000 only has 2 significant digits and we're dividing or multiplying, my final answer must only have 2 significant digits. So I found a way to round it off, and the 6 told me to round the 0 to a 1. Okay, so that's how I ended up with that. Okay, 510. Okay, you guys, so this will be the video for 3C, and then I believe we're going to have our test coming up pretty soon. So this will be the last video for this chapter before the exam. Okay, that'll do it, you guys. Thanks for watching, and we can talk about the exam in our next meeting. Okay.